We're live. Welcome, everyone. We're going to get started here in about 2 more minutes. So for those of you that just joined, welcome to today's webinar. Like I said, we'll get started here in about 2 more minutes. All right, looks like we've got some more folks who just jumped on. So for those of you that just joined, we'll get started here in about 1 more minute. All right, let's go ahead and get things started here. Do you want to get a little bit of feedback first? So I know we got quite a few people that just jumped on board. So what I'm going to do right now real quick is activate the raise hand feature before I do my little housekeeping here. Quick show of hands here. So for those of you that just jumped on board here, quick show of hands here. Please raise your hand if you are a teacher participating with students. So click on the raise hand feature if you're a teacher participating with students in the same room there. So if we look at the raise hand feature here, we got people chiming in. So about, what do we have here? 6. So 6 people here are joining with students here. All right, awesome. All right, just wanted to get that out of the way here real quick. And we'll be launching a poll a little bit later on, so be on the lookout for that. Let me go ahead and disable the raise hand feature. All right, let's go ahead and get things started here. So welcome everyone to today's webinar, Chasing Black Holes. My name is Raul Montez. I'm on the marketing team here at Zoom. I'm actually located at our headquarters here in downtown San Jose. I'll be kind of working in the background in case you have any general Zoom questions. Before I pass things over to Jim Sigmund here, just want to do a little housekeeping. Do want to point out that we are using the webinar platform to host this webinar. So if you have any questions, go ahead and send those in through the Q&A panel. We'll have a Q&A session at the very end of the webinar. So send those questions in. We'll try to answer as many as possible. Also want to point out that we are recording today's webinar. So be on the lookout for a follow-up email with the link to the recording. Like I said, we'll send out a follow-up email with the link to the recording and also some contact information in case you want to reach out to our presenters today. But having said that, what I am going to do right now is pass things over to our very own Jim Sigmund to kick things off. So Jim, go ahead and take it away.
Good morning, folks on the West Coast, and good afternoon to everybody else. My name is Jim Sigmund. I am a account executive at Zoom. I focus exclusively on K-12 and Zoom support in that area. Welcome to today's webinar, Chasing Black Holes, the quest to find, photograph, and understand black holes. We at Zoom are really proud to do our small part to bring this nationwide educational webinar to your homerooms and classrooms and homes and desktops. This project and the research grant that supports it is sponsored and supported by the National Science Foundation. Your teachers today, which you see, will see online, are Doctors Feryal Ozel and Dr. Dan Marrone. Feryal and Dan are members of the Event Horizon Telescope Collaboration, which uses an array of 9 telescopes across the Earth and aims to provide the first ever images of 2 black holes nearest our galaxy. Feryal and Dan are also primary scientists contributing to the Black Hole PIRE project, which supports student education, which is certainly our goal today, and technology development in order to increase global sharing of data, tools, and resources. Feryal is a professor of astronomy at the University of Arizona. She made pioneering contributions to physics of neutron stars and black holes and works with NASA and the Chandra X-ray telescope, among other projects. Feryal is interested in sharing this field of black hole science with students of all ages. Dan Marrone is also professor of astronomy at the University of Arizona. He's interested in topics in galactic and extragalactic astronomy, including galaxy clusters and their cosmological applications. He develops telescope instrumentation, and really interestingly, Dan spends time at the South Pole each January on this project. So you are in great hands with these 2 professors and scientists, and enjoy the webinar.
Thank you very much, Jim, and thank you everybody who's joining us from their classrooms and homes. We are very thankful to Zoom and to our sponsor, the National Science Foundation, for allowing us to bring this educational content to you. We are going to, my colleague Dan and I are going to talk to you about the exciting chase for black holes that we've been engaged in both at the University of Arizona, but with a worldwide collaboration. And what we are hoping to do is take you on a journey through the laws of gravity, how we understand gravity, how we search for black holes, why they are mysterious, and what we are hoping to do with this project. And in the meantime, take you through the various methods of astronomy that we routinely use, whether on this project or on the other observations and quests that we go through. So Dan is going to get you started on the first rule of astronomy, which is choose the right wavelength. Dan.
Right. So this is a presentation in 4 parts, and the first part is figuring out how we might observe black holes. So when astronomers look at the sky, we have many choices of how to observe the universe. Light, we usually think of as light we can see with our eyes, but it's actually a much broader term that covers the entire electromagnetic spectrum, which is all types of light that exist. You can describe light by many ways. I think in this talk we will talk primarily of its wavelength, but you can equivalently describe light in terms of its frequency or its energy. Visible light is a small fraction of this. In the figure you can see sort of to the right of the middle, there's visible light, but extending for factors of many powers of 10 in any other direction in wavelength, there are other kinds of light, including radio waves, X-rays, gamma rays, infrared. And these are all just forms of light, even though our eyes can't perceive them. In astronomy, we choose which form of light we're using to answer specific questions. So take black holes as an example. We can look at them at different wavelengths and observe different aspects of them. This is an X-ray image of the galaxy Pictor A, and you see a very bright point at the center, which is actually emission coming from the region around a black hole. You also see jets of light and a cloud of emission. If you look at this same object with radio waves, you see that the black hole is still there, the bright point of light at the center, but now there are lobes of plasma emitting radio waves that were because these electrons were emitted by shot out by the black hole. And so we combine these multiple images to learn different things about how that black hole is interacting with the galaxy it lives in. In the case of studying black holes for this project, we have another constraint that we have to consider. The Earth's atmosphere doesn't let all wavelengths of light through it. That's good, because if it let, for example, X-rays and gamma rays through, we would never have evolved to exist, because those things would sterilize life on Earth. But for astronomy, that can be a problem. Observing with X-rays has to be done from above the atmosphere. You can see in the figure that visible light gets to the ground, which is why our eyes evolved to observe it. But radio waves also get to the ground. And so when we choose how we want to observe black holes, it's much easier for us to construct our telescopes on the ground. And so we're forced to choose either visible light or radio waves.
So we already said we are looking for black holes. We're looking for the emission around black holes from their regions. But how does one go about establishing that some object that we see in the sky and that we can measure in some different wavelengths is a black hole? You might think that's a difficult problem, but actually we use the same laws of physics that we use right in our own solar system. So the principles of looking for a black hole are no different than understanding how planets move around in our solar system. And I will explain how that goes to you. So we know that the earliest observations of the motions of planets in our solar system, the complete observations, were done by Tycho Brahe. And the famous astronomer Johannes Kepler in the 16th century used these observations to establish empirical laws about what keeps them in place and how the orbits of these planets, the time that they take to complete these orbits, and how distant they are from the center, which he established to be the sun for the center of our own solar system, relate to the mass of the sun. So in the animation here, you're seeing the inner planets orbiting around the sun, and you see that the slower ones on the outside have the bigger orbits, and the faster ones on the inside have the smaller orbits. But Kepler, using these data, actually established the relationship, a precise relationship between the square of the orbital period, which in this expression is shown as t for time, and the cube of the semi-major axis, which here is shown as a. So if you look at the plot shown on the slide, if you plot the cube of the semi-major axis against the square of the orbital period, so for the solar system objects like Earth and Mars, etc., our orbits are almost circular. So you can think of the semi-major axis as simply the radius of that circle. If it's not a circle, if it's an ellipse, then you just take half of the major axis of that ellipse. And you see that they all line up in a very tight relationship. And when you plot them against one another, you can also determine the mass of the sun, which is holding all of these planets in orbit. Now, you might think this is specific to our solar system. Maybe something special is happening here, but that's not really the case. This is the empirical formulation of what we later understood to be simply the law of gravity. So anywhere in the universe where we encounter gravity, this type of law should apply to orbiting objects. This is because Newton, about a century later, formulated gravity as an attraction between two masses. And he said the force with which they pull on each other is proportional to the mass of the two objects. So in this particular case, it would be the sun and the planet. But it could really apply to anything. It could be two stars in a binary system. It could be a black hole and a star. And as long as the gravitational force is holding that object in its orbit, we should be able to apply it. And this is really convenient. This allows us to not only find black holes, but precisely measure their masses. So what this animation is showing you actually, this is an animation of real data. So in some cases, we make computer simulations where we are simply running our models. But in this particular case, I'm going to run this for you one more time. What we are looking at are stars, actual observations of stars in the center of our own galaxy. So this is the Milky Way, our own galaxy. We're looking in the center of the, we are looking in the direction of the center with very powerful telescopes zooming all the way in, and we can identify individual stars. Not only that, but we can do this year after year after year, just like Tycho Brahe did it for our own solar system planets. We are following the orbits of these stars around. And when we combine all these data, you can see the clock running on the upper left corner. This experiment has been going on for nearly 20 years. You can see the complete orbits of some of the stars that are close to the center of our galaxy. The red cross here marks the center. So I'm going to zoom in a little bit more and now show you a still image of what those orbits look like. So these are the two closest stars that we were able to find, called S2 and S102. And their orbits are, these are again actual data. They are marked with these dots that are taken over time. And just like we looked at the solar system planets and said, what is the mass of the central object holding these in place? We can apply the exact same law, Kepler's law, to these data and ask, what is the mass of the thing that is holding these stars in their orbits? And that mass turns out to be 4 million times the mass of our sun, okay? Now, it is a dark object. Notice I didn't say a black hole. It is a dark object that has 4 million times the mass of the sun. Why am I calling it a dark object? Well, first of all, there's very little light coming from that center where that cross was. Second, if we just asked ourselves, well, what if this was a normal star, 4 million times the mass of our sun, and take it to the distance of the center of our galaxy, how bright would it be? It would be 10 billion times the brightness of our sun. And I don't mean just where it is. It would appear to us 10 billion times brighter. So it would completely overwhelm what we're seeing in the galaxy. Clearly, that's not happening. In fact, it is a teeny weeny radio source, okay? So is it a black hole? Well, we call an object a black hole, first of all, when it's relatively dark, very massive, and occupying a very small volume. In the fourth part, I'll come back to a more exact definition of what we would call a black hole. But right now, basically, we can measure its mass, we can measure its size, size as in it has to fit inside the orbits of these stars. And we want to know if it's truly the black hole that Einstein's theory of general relativity predicts. So how would we go about this? We have these beautiful data, but we don't have direct evidence of the black hole. And that's what motivated the Event Horizon Telescope project. We want to be able to take an actual picture, an image, and you might think an object that has 4 million times the mass of the sun is very large in the sky. That is not the case because it's so compact, so much mass in a small volume. It actually has a very small angular size, which is what Dan is going to tell you about. And we also want to look, again, as he was describing, in the right wavelength. The material around the black hole emits in the radio wavelengths, so that constrains us, right? Trying to see a small angular size in the sky in the radio wavelengths. How are we going to do this?
So to do this, to see something as small as this black hole, we need a special telescope. If you think of a black hole as an incredibly big object, remember this object has 4 million solar masses to it. you might expect that it should be relatively easy to see. In fact, the diameter of Sagittarius A Star, this putative black hole at the center of the galaxy, should be 9 times larger than the diameter of the sun. But it's also 2 billion times further away than the sun is. And so if you combine those two facts, it turns out that this black hole appears very small in the sky. The angular size of an object, the size it takes up on the sky, is determined by both the size of the object, its diameter, and its distance. You can see this in the figure. I have 2 different black hole-like objects, 2 gray things at 2 different distances. They both have the same diameter, small d, but the angle, drawn in blue for the near object and drawn in red for the far object, is different. The farther object is much smaller. This is extremely familiar. You know that as things move away from you, they appear smaller. So what does this mean for looking at this black hole? Well, if we put in the distances and the diameter for Sagittarius A Star, what we find, this black hole at the center of our galaxy is 28,000 light years away. If you convert that to a more familiar unit, rather than the distance light travels in a year, the light year, it is a very unfamiliar 2.6 times 10 to the 17 kilometers, or 260 million billion kilometers. It sounds like a made-up number, but it's just far away, right? Its diameter is 62 million kilometers, again, about 9 times the diameter of the sun. And so if it were in our solar system, it would take 9 times as much space on the sky as the sun does. If we put these numbers into that equation that's shown there, theta is the angle in degrees, we find that Sagittarius A Star is 14 billionths of a degree across. If you hold your thumb at arm's length, that's about 1 degree across. So it's 14 billionths of the width of your thumb held at arm's length. Astronomers like to talk about something called arc seconds. So there's 60 minutes of arc for every degree on the sky, and there's 60 seconds within every minute of that degree of arc. And so Sagittarius A Star, we normally say, is 50 micro arc seconds across. For comparison, the Hubble Space Telescope, something we think gives us incredibly sharp pictures, has a resolution of 50 milliarc seconds, or 1,000 times worse than what we're talking about here. So again, Hubble itself is a very special telescope, but it is not the right telescope for this job. What do we need? Well, we need a telescope that has higher resolution. You can get higher resolution by increasing the diameter of your telescope, or you can get it by going to a shorter observing wavelength. Both of those factors determine the telescope resolution, according to that equation right there. We talked about how we're constrained to observe only things that we can see through our atmosphere. So we could look in visible light, but it turns out that the galaxy blocks the visible light towards the center of it, or we could observe at radio wavelengths. We want to go to the shortest radio wavelength we can because that improves our resolution. But even if we do that, if we observe at about 1 millimeter, which is about what our atmosphere allows, we still need, using that equation, a telescope that is at least 4,000 kilometers across to get 50 microarc second resolution. The Earth's radius is 6,400 kilometers, so we're talking about a telescope the size of the Earth. And that's in fact what we've been building. The Event Horizon Telescope is a telescope that spans the entire Earth. These images have the telescopes marked, so we extend all the way from Greenland in the north, through Arizona to the South Pole in the south, and all the way from Hawaii in the west to France and Spain in the east. We cover the whole globe, and we get resolution that's good enough to try and take a picture of a black hole. Some of the excitement of this project, at least for those of us working on it, is actually making it happen. As Feryal said, part of that process has been making each of these telescopes participate. Here are pictures of the South Pole. It's a beautiful place, and you should go if you ever can. But at all of these sites, we've had to get receivers ready, get mirrors ready, get recording equipment ready, and get everything tuned up so that we can all simultaneously observe the center of the galaxy all over the world. And these are images of people from us doing this for the first time in 2017. If we can do that, we can take the data we record at each station, bring it back to one place, and with a supercomputer, reconstruct one telescope that is equivalent to one the size of the Earth. And so now Feryal can talk about what we can do with that.
Yeah, so as you can see from what Dan is describing, this is a long and a lot of effort. So what is it that we hope to see? What should a black hole look like? What would make us say, yes, that dark object with that huge amount of mass in a compact space is actually a black hole according to Einstein? So we talked about Kepler's laws. We talked about how Newton formulated them into a law of gravity. Well, then came Einstein, right? In the early 1900s, he started rethinking about what gravity might be. We, until that point, had been describing gravity as masses pulling on each other, just like in Newton's forces. But Einstein had a very different way of thinking about it. He said, actually, this mass and this mass, they're not acting on each other. Rather, what they're doing is they're warping the space and time around them. Okay, what does that mean? So it's very difficult to visualize how a mass might actually warp space, let alone time around it. But one way to kind of think about it is something we're familiar with. If we stretched a sheet and put a mass in the middle, it would actually sink down and form a little bit of a curvature around it. So if we represent time and space as that sheet, which is shown in this green grid on this image, and think of every mass or energy, in fact, it could also be energy, it doesn't have to be a mass, making a dent in that space and time, it is how Einstein formulated it. So the main difference in how we think of gravity according to Newton and according to Einstein is how things move in this warped space and time. Most importantly, what happens is light follows paths. We know that when you shine light, it follows straight paths. Well, light follows paths that it thinks is straight on this curved space-time. But because the sheet itself or the space itself is curved, what light does is follow the curve down and then back up and then continues on its path for most objects. Here, the mass that's warping the space is the sun. We are standing on the Earth and we're looking at a star that is behind the sun, okay? So let's say that the position of the star is shown in that yellow, with that yellow trajectory, and it's to the right. So light leaves that star and follows its path, just like it always does, and reaches us on Earth. But when we look behind it, we think that it is actually coming from, because the position, because the path was changed, we think it's coming from a star that is shown by the red trajectory. This might sound a little bit confusing, but actually this is what happens all the time, right? We're familiar with light being bent and changing paths just by a full glass of water, or even when we put our face in a pool, or by any lens for that matter. So when light changes trajectories, we think that it is coming from a different direction, just like the cat's eyes here appearing in a different place. So this is a central concept of Einstein's theory. How does this relate to black holes? Well, all masses warp space and time around them, but black holes are a special type of compact mass that warps space so much that they don't only change the paths of light, but they make it so compact light gets trapped inside of it. So if we were shining light on a black hole, if light is going towards the black hole at a comfortable distance, what it will feel is the trajectories that you're seeing, like those paths that you're seeing in red in this animation. This is an actual computer solution of Einstein's equations that tell us how light moves around a black hole. So if it's a comfortable distance from the black hole, its path will get bent, but it will keep going. If it happens to be too close, which are the rays that you're seeing in blue, they're going to be bent so much that it's almost going backwards and being trapped inside the black hole. And that is going to leave a characteristic hole that is black in the middle of the light around it. So black hole actually is not a very creative name when you think about it. It should literally look like a black hole, like the one you're seeing on the left. Of course, there's nobody with a flashlight shining light on a black hole, so we on Earth can set up our experiment and see it. But there is enough material circling around the black hole that is fed by all the stars that we just saw, right? All those stars in orbit, because black holes' effect on them is so strong, there's all this material falling onto the black hole, and en route to this darkness, it actually emits light in the radio wavelengths. So this is precisely what the Event Horizon Telescope is trying to see. And if we have a couple more minutes, I'm going to show you how we go from that one simple calculation to more sophisticated calculations that we have to do in order to get ready for the observational data that we're collecting. So I hope you can see the details of this. This is a video. Let me describe the setup to you, and then I'm going to play it. This is on a laptop, and we are seeing the monitor. We are also seeing a hand, one of our colleagues here at the University of Arizona, controlling a simulation. So real-time solutions of Einstein's equations. And this particular solution is done on graphics processors units, just like what you have on your phone or on your computer. And it allows us to solve these equations extremely quickly. So instead of typing in commands, he's using a leap motion device, which you can see right below his hand. It's a small black rectangle appearing there. And what we do is initialize the simulation, and he's running time forward, shooting 1 million rays of light onto a black hole and calculating each and every one. What happens? Which ones get scattered? Which ones get trapped? You see already that a lot of them got trapped and made that little halo around the black hole. But some of them actually we're not even seeing because they fell in already. So if we look at it on the larger scale again, when our colleague CK pulls back, you're going to see that in that wall of light, what it left is an unmistakable print of what a black hole should be, which is the black hole in the center. So in about 5 seconds, you're going to see what I'm talking about. When we zoom out, we're going to see the hole that should appear if these objects really behave the way that we think they do. So in parallel to all the work that has been going on at telescopes, all the instrumentation, observing, we've also been working a lot on trying to understand what the environment of the black hole at the center of our galaxy is like. How much gas is it getting? Are there any circumstances in which we wouldn't see the black hole in the image? And here are 6 different manifestations of our attempts to model it. And what you will see is that even though the distribution of the light part around it varies from maybe one scenario to the other, in each and every case, the black hole actually appears in the image. So this is what we're after. We've had 2 observing runs. We're gearing up for the 3rd one in March of 2019. We're working on all the data. We're working on combining them. And we want to have a definitive, very high angular resolution picture of the first one, in fact, of a black hole, both in the center of our galaxy and in a nearby galaxy called M87. And we want to have this definitive proof that will tell us if Einstein's formulation of gravity near black holes is correct. So we want to leave you with some updates that you can follow. Both the PIRE project and the Event Horizon Telescope have websites that you can follow our news on. There's also a Twitter and a Facebook account that you can follow. And with that, I think we'll stop and take questions.
Maybe we will, as soon as I figure out how to do it.
There's a question that came in. What is the brightness scale measured in the last panel?
Go.
Okay. So the question is, what is the brightness scale measured in these images that I'm showing? It is arbitrary here. Of course, we normalize it to all the other constraints we have on the black hole. For example, we know that in the radio wavelength, it's not very bright. We know that it has some X-ray emission that we've been able to follow with the Chandra X-ray telescope. So even though in these images, the brightness scale is kind of arbitrarily normalized, in real life, we have a very good idea of how bright these things actually should be. And what we're looking for is the contrast between the bright part coming from the gas around the black hole, the surrounding material, and the blackness at the center. And that contrast is very large, so that's what we're looking for.
But for reference, in radio astronomy, we have a unit of brightness called the Jansky. The sun dumps about 100 watts of light on every square meter of ground on the Earth. You know, the brightness of an incandescent light bulb, I guess. The Jansky unit and the black hole emits about 4 Janskys. The Jansky unit is 100th of a billionth, no, 100th of a trillionth of a trillionth of a watt per square meter per unit frequency. So it's pretty faint, it turns out, which is why we do this with big telescopes.
All right, another question. Do you feel like black holes are properly represented in Hollywood movies?
Oh, that's a very good question. Black holes actually appear in a lot of Hollywood movies, including animations. And I would say that the one that made the most sincere attempt to represent black holes accurately was Interstellar. And there, just like we are running these computer simulations for the Event Horizon Telescope experiment, the scientific team on it also did a limited number of simulations in order to represent the black hole accurately. The one thing they did not do, and I think on purpose, is this asymmetry. When you look at these images, these set of 6 that we're showing here, you will notice that one side is brighter than the other. That's because when gas swirls around the black hole, there is an effect called the Doppler effect. We actually experience this in our daily lives. When an ambulance is approaching us, it is a sharper sound and it is louder. When it's receding from us, it's dimmer. Same thing happens with light. When light is emitted as something is approaching us, it looks brighter, and it looks dimmer when it's receding from us. So that's why, even though the gas around it is kind of circular, in the actual images, one side looks brighter than the other. Interstellar didn't show this, not because they didn't know about it, but they probably didn't want to confuse people. So yeah, at least in the recent movies, there's a real attempt.
Another question, do the huge telescopes require a person to be there to operate it, or is it all by computer?
At all of the sites, there are people to operate them, not least so that no one wanders by and gets crushed by them. There are astronomical telescopes that get run entirely by computer, but these are big and expensive facilities, and it's worth having someone working on them in person.
And if something goes wrong, to be able to just,
But also the thing
Try
about the crushing people, that's no good. So.
yeah, that is really no good, that's true.
Another question here, is there any new data about the jets being emitted out of some black holes? Have you or anyone done any simulations with these jets?
Yes, we have. There is, so what this question is implying is when we look at black holes at larger scales, we see that some of them emit jets, like the example that Dan showed in the beginning, radio lobes and X-ray jets, and some don't. We don't really know what the difference between them is. Actually, that's one of the questions that we're trying to address with the Event Horizon Telescope. Are there new data? Yes, there are ongoing observations in multiple wavelengths. The Chandra X-ray telescope is making really detailed images of how these jets vary in X-rays and what is the scale of them, and same in the radio. And in fact, of our two primary targets, the one at the center of our galaxy, Sagittarius A Star, according to all the data that we have so far, does not have a jet, whereas the black hole in M87 does have a really large-scale jet. So simultaneous with our own observations at the millimeter wavelengths, we've asked our colleagues around the world, we've asked telescope directors and our communities to go ahead and observe these black holes when we are also looking at them. So New Star and Chandra and Fermi and ground-based optical telescopes, they all try to help us out and try to get the jet data at the same time that we were getting the high resolution data.
Another question here, how did you discover the black hole?
So Sagittarius A Star in our galaxy was discovered almost 50 years ago now. The idea of black holes, and the idea of black holes is very old. The idea that there might actually be black holes in the universe is not as old. And so in the late 60s, people started to observe bright points of light that they were suggesting might be emission from around black holes. And a group of radio astronomers at the National Radio Astronomy Observatory started looking toward the center of our galaxy, where there's a very bright radio source that had been known since the beginning of radio astronomy in the 40s. And they noticed that it too had a very bright point of light at its center, and they called that Sagittarius A Star, the stellar-like component within Sagittarius A, the brightest radio source in the constellation Sagittarius. And ever since, we've been making sharper and sharper pictures and watching stars go around it and concluding that it is very likely a black hole.
I should just qualify something you said. You said a very bright source. Of course, that's a relative term. It is a
That's
very dim source. It's just bright compared to what is around it.
That's right.
Yeah.
Another
A question, are all the telescopes the same aperture or are they different? And if different, how does that affect any imaging?
So they're all completely different. We're just using whatever telescopes we have available. So the smallest telescopes in our array are 10 meters across, which isn't that small, to be honest. The largest single telescope is 50 meters across, and that's in Mexico, a large millimeter telescope. And some of our telescopes are even arrays. ALMA in Chile is an array of 66 telescopes that are each 12 meters across. And so we can combine all of those things. Fortunately, all we care about is what they see at the very center of their field of view. So if you have different individual telescopes, they see different size patches of sky. But remember, we're only looking at the inner 50 or 100 micro arc seconds, which is a tiny fraction of the patch of sky they see, so it doesn't matter all that much.
As long as we collect enough light in all of those stations to be able to see our source, the combining works afterwards. Yeah.
Another one here, how is the mass of black holes created?
That's a good question.
That is a good question. What we find out as we study black holes in the universe is that they are actually one of the early residents of the universe. So shortly after the Big Bang, as stars were forming, so were black holes. And in fact, they grew in some cases even faster than the galaxies that grew around them. We don't exactly know how. We still, there are outstanding questions about whether it was individual stars that created the black holes or clusters of stars or even something larger. And the initial collapse that happened to create these, what we now call supermassive black holes in the centers of galaxies. It must have been from some mass, whether this was a star, clusters, we don't know yet. We need more sensitive telescopes that can see farther back in time in the early stages of the universe, what those were. Over time, they grow either by merging with another black hole, but even more strongly by just wandering stars around them and absorbing some of the mass and light from those stars, and that just contributes to the mass of the black hole. So over time, it grows through a process that we call accretion, which is getting mass and light from its surroundings, or through mergers, which is finding another black hole and over time spiraling in, just like the event that we saw with the LIGO observatory, and growing in mass that way.
Should we take another one? What do you think about the white hole idea? I mean, we don't have any astronomical evidence of anything like a white hole, which is sort of the other end of a black hole, the place where material that falls into a black hole could reappear in the universe. So it isn't astronomically important so far, and so I don't think about it very often.
Mm-hmm. Yeah, in physics, this is something we encounter often. We write down equations that that represent that system, and we find mathematical solutions to that equation. And some of those solutions actually make sense, they're applicable to nature, and others don't appear in nature, either because they violate something that we know, something else that we know about, or because they simply don't have a representation. And white holes are likely to be in that category.
One more. All right. The question is, in theory, is it possible for a curved black hole to generate a measurable gravitational wave? We should unpack that a bit.
Yeah. So a black hole generates gravitational waves when the space-time around it changes. When would space-time around it change? In the case of the black holes that LIGO saw, for example, it was two distinct black holes that were formed from two separate stars that were in orbit around one another. And over time, their orbit shrinks. And as this orbit shrinks and the masses come closer to one another, that fabric, that curvature in the fabric that we talked about in Einstein's theory, keeps on changing. When that happens, the black hole emits, so in order for the orbit to shrink, it keeps on emitting gravitational waves. It certainly is measurable in that particular context. For example, when we have a 50 and a 40 solar mass black hole orbiting one another and eventually merging, that causes a relatively big signal that the LIGO telescope was able to see. If a small mass is falling into a black hole, it also generates gravitational waves. It's a ripple in that space-time. However, we don't have right now the technology to be able to detect that. What that would take, especially around a supermassive black hole, is the space-based observatory LISA, which would be sensitive to different types of gravitational waves, different frequencies, different amplitudes. And there, even when a smaller object falls into a large one, we would be able to detect it.
But if you just have a curved black hole, which is just a spinning black hole, it doesn't create this disturbance in this, any changing disturbance in the space-time around it. And so on its own, it won't create gravitational waves.
That's right. If it's just sitting there, there is nothing that's changing, so it doesn't keep on emitting these waves. It just sits there.
Okay.
All right. Well, thank you all for joining us. We want to thank again the National Science Foundation for supporting this work and our PIRE project and all these educational opportunities, and our partnership with Zoom. We hope to keep on bringing these webinars to you. And just to wrap up, for this particular webinar, Dan and I also created an instructor guide. So if you joined us from a classroom, or even if you joined us as a lifetime learner, this is a PDF file that was mailed out to all the participants that registered for this webinar. There's a little bit more information, a couple of follow-up questions if you're interested in doing that. Thank you.
Thank you.
All right, folks, thanks for joining. Don't forget, we are recording, so we'll make sure to send out a follow-up email with the link to the recording. But having said that, thanks again. Bye, everyone.